Welcome back to 3 Deviations. Today's video 14 of multivariable calculus, and today we want to talk about curvature of vector functions. Now, curvature is a very important topic in vector functions because it tells us how curvy something is, how curvy our vector function is. So in today's video, we're going to look into curvature, we're going to do an example or a couple of examples about curvature, and then we are going to call it a day for at least all of the theory we need to know about vector functions. Note that we still do want to apply them later on. Now, my heading here says definition, but what it really should say is definitions, because we have a lot of definitions to cover. We can define the curvature as kappa, and kappa is equal to the derivative of the unit tangent vector with respect to the arc length, or the arc length parameter. Now, we can actually rewrite our dt by using our definitions of chain rules. So we can define this in terms of our parameter t as opposed to our parameter s. So we can note that dt by dt is equal to ds, or dt ds by ds dt. So thus we can redefine kappa as being equal to the magnitude of the derivative of the unit tangent vector with respect to t over the derivative of the arc length with respect to t. Now, if you note, we can make this more simple because we remember that this is actually the formula from the last video. Remember, that's the formula for the derivative of the position vector. And obviously, we can use Newton's notation for the upper part. So thus we get kappa as a function of t is equal to the magnitude of the quotient of the first derivative of the unit tangent vector over the first derivative of the position vector. We can also write this in completely in terms of the position vector, such that kappa of t is equal to the magnitude of first derivative of r crossed with the second derivative of r over the first derivative of r magnitude cubed. And we can take this one step further in case we want to use curvature to define the actual curvature of a real valued function. So say I have like a parabola. If I have a parabola, that was a horrible parabola. Let's draw a tangent line. If I want to find the curvature of this function, then I can use the following formula such that kappa as a function of x is equal to the magnitude of f prime of x over 1 plus f prime of x squared, all to the 3/2 power. All right, let's actually apply the idea of curvature now to an example. So for this one, I would like us to find the curvature at a general point of r of t equals t squared and t cubed. Okay, so we're just going to use the formula that we found earlier. What you're going to notice in these examples is that we need to find a lot of different ingredients in order to solve our problem. So first, what we're going to want to find is our derivatives. That's pretty easy. We already know how to take derivatives of vector functions. The first derivative is 1, 2t, and 3t squared. The second derivative is 0, 2, and 6t. Should be fairly simple. And now we want to find the cross product of the first derivative with the second derivative. Now, to do that, we take the vector product by using that determinant method, or you could have just remembered the vector formula, but we get 6t squared, negative 6t, and 2. Now we want to take the magnitude of this guy. Excuse me. So to take the magnitude, we just sum all of the squares and then square root. So we get 2 times the square root of 19 fourth plus 9t squared plus 1. Okay, so now what we want to do is we want to find kappa of t. Now, kappa of t is equal to this here, and then we also cube this there as well. So what we get is we get 2 times the square root of 19 fourth plus 9t squared plus 1 over 1 plus 4t squared plus 9t4. And that's all to the 3/2 power. All right, now we would like to move on to another topic, and this topic is called the normal unit vector. So we talked about the normal tangent vector, but what if we want a normal unit vector, or we talked about the tangent unit vector. So if we have a vector function like that, we have a tangent vector, unit tangent vector, we also want a unit normal vector. Now, by nature, these will be perpendicular and can form some orthonormal basis. So we define the normal unit vector, as the derivative of the normal tangent vector over the magnitude of the derivative of the normal tangent vector. We can also define the binormal tangent vector, or the binormal unit vector, as being the tangent unit vector times the normal tangent vector, times the normal unit vector. My gosh, there's a lot of words here. Anyways, let's try an example with this one too. We're going back to our old friend the helix. I want us to find the normal and binormal vectors for the helix, parameterized by r of t equals cosine t, sine t, and t. Okay, so now to do this, we just need to find all of our ingredients. Find the magnitude of the derivative of this. We've done that earlier. We've determined its root 2. Take the derivative, square all of the, sum all of the squares. Just take the square root. Use the Pythagorean theorem in there. Now, to get t of t, or to get t of t here, we divide by the magnitude. We divide the vector by the magnitude. So we get 1 over square root 2, negative sine t, cosine t, and 1. Now we want to find the derivative of that vector. So it's still 1 over root 2, but now negative sine goes to negative cosine. Cosine goes to negative sine, 1 goes to 0. Then we take the magnitude of that, we got 1 over rad 2. Finally, we find the normal unit vector, and we get negative cosine t, sine t, and 0. And now